So good afternoon. My name is Andri and I'm Stefánsson, those of you who don't know me. So I'm here at the University of Iceland with a specialty in geochemistry. So today I'm going to talk a little bit about H2S, hydrogen sulfide, and then related to a project of how we can possibly sequestrate H2S into geothermal systems. It's a project partly sponsored by the GEORG, that's why I'm here, but there are other partners as well. I'll come to that in a minute. So why are we doing this at all? So basically the thing is that sulfur in general, in different forms, is a major component, it's a major element in geothermal water and geothermal vapor. And it's one of the key elements that actually we bring up from the ground to the surface with the fluids. And because of this and utilization of geothermal fluids for energy production, there is a considerable release of these elements, including sulfur, into the environment. This is basically in terms of both in the water phase, but mostly in the steam phase. So you can see here's the mouse. So this is just, for those that don't recognize this is the Nesjavellir geothermal power plant. Don't know why I chose this one, it's just a beautiful picture. But this is the general thing. So you have the steam going out, it's mostly water, but there's also a lot of other things there, mostly H2S. We recognize that from the smell, okay, we all know that. And then, but it's mostly CO2, there's also hydrogen and other things as well. And in the fluids, the concentrations of these major components, including the CO2 and H2S, and this is what we're going to focus on today, this one here, is quite high, up to maybe 2,000 ppm CO2 and 500 or even higher ppm, milligrams per kilogram of fluid of hydrogen sulfide. So, and this is simply just emitted mostly in most places, at least in Iceland, straight into the environment, mostly in the steam form. So it's coming out here, and as I told you before, I mean, we all know, we smell this basically. And it's transported with the plume depending on the weather direction. Sometimes it comes to Reykjavik, sometimes it goes to Hveragerði in the case of fengið area, and it's the same story in other geothermal locations in Iceland. Okay, so there is a growing concern about this, mostly because of environmental issues. So H2S, it's actually a poison. So it's not only a bad smell, it's also a poison. It can also affect a lot of the vegetation and environment, groundwater quality, air quality, and so on. And after all, it's a poison, and actually I'm not so sure that people are generally aware of that, but hydrogen sulfide is a stronger poison than cyanide. So you actually, if you get too much of H2S, you can simply just faint and eventually possibly die. So this is nothing new. H2S, environmental issues related to H2S is a very common problem, not only in geothermal energy utilization, but also in the oil business. And so people have been fighting for a long time with how to get rid of this in a costly and an effective way. And most of this are related to do something on the surface. So there are various types of reactions that are triggered. Maybe the best known is the Klaus process, which is utilized a lot in the oil business particularly, where you convert the H2S to another form of sulfur. This is, however, often difficult to operate, expensive. You get a waste that you don't know what to do with. You get sulfuric acid or sulfur. You can maybe try to sell it, but in some cases you just have to pile it up on your site. And sulfur mounts is a common problem, for example, in North America today. But in geothermal, one way of dealing with this, and this is an idea that came up here in Iceland maybe 5 to 10 years ago, is one possible solution to this is actually just put it back into the system. So basically what people are then thinking of, it's not only re-injecting the water back in, but it's putting the gases as well into the re-injection fluid, like you heard about the previous talk, and then you basically put it back in. So what you end up getting is some kind of a closed loop in terms of not only the fluid, but also in terms of the elements in the fluid, and then we are mostly thinking of the H2S. So basically what you have, basically what you have is you have a production well here, and then it goes into your power station. Well, it's the other way around, production well goes into your power station, and then you have your reinjection well. And then you re-inject the H2S together with the fluid instead of just releasing it into the atmosphere like we mostly do today. I'm not going to talk about the engineering aspects of this. There's a huge challenge in the engineering aspects of how to take the gas and put it back into the fluid and then injecting it back in a safe and an economic way. But I'm more going to talk about the chemistry part in this, because the thing is, the H2S is re-injected into the ground here. It comes up, we produce the electricity and whatever we want to do, and then we re-inject it into the system, and then the H2S, well, that's at least the idea behind it, can mineralize within the system. So we're actually not doing anything except just enhancing the natural, let's say, alteration of the geothermal system, if you want to say it in that way. So basically, it's a simple thing. When the H2S is back into the system, dissolved in the geothermal water, it will react with the surrounding rocks, that's at least a conceptual view of it, forming different types of sulfides. So it's permanently, at least if the sulfides are stable, it's permanently just basically fixed within the altered rock at depth. And it'll stay there until something changes in a way. So you can say that what we're trying to do is making an ore deposit. We're trying to make a sulfide type ore deposit. And this is actually the way a lot of sulfide type ore deposits are actually formed. You're just, in a way, enhancing it. So basically, after this idea came up, there are several questions we want to try to answer before we try. Because in case something goes wrong, then we may be in a serious trouble in terms of that we have somehow affected our system, we have changed the permeability, we have changed the composition of the fluid that possibly is coming up, changing the utilization cycle, and etc. So this is what this project is all about. It's basically divided into then 3 parts. It's to study, you can say, the background level in this geothermal system. What is the geochemistry of H2S, hydrogen sulfide, in the geothermal systems before we start to play with it? So this is, you can say that this is the baseline or the background understanding. So this is a critical thing to understand. The second thing is that then we have to add the next layer. So the next layer would be basically to understand how the system, in terms of here the geochemistry, or the chemistry and the mineralization, will respond to our injection of the fluid containing all this H2S. So this is something that we want to try to then answer. Is this something that will happen, or is, for example, the H2S, will it just come back into the producing wells? And then based on this, we have some kind of an assessment of the feasibility of the whole thing. And this is a little bit where we stand today. We stand at the last thing here, the last 2 parts here. So I'm going to give you a brief introduction of how we approach this problem. Again, it cannot be applied to any other geochemical problems in a similar way, but this is the general approach. So the general approach that we always try to somehow apply to things like this in terms of the geochemistry is that we have a key question to try to answer. That would be the geochemistry of H2S, and have some kind of a conceptual and quantitative understanding of what's going on. So basically what it means that we understand our system either disturbed or undisturbed. The way we do that is that we try to study natural systems. We can call that natural analogs. We try to do computational work, do it on the computer, that is cheap and relatively easy to do, but there may be lots of uncertainties to that. We try to do downscale laboratory experiments. We try to mimic the system, and then in the case of sulfur, there's an analytical chemistry component to this because the sulfur chemistry is quite complicated. So basically, we want to approach the same problem from different directions and hope to get an overview or a conceptual understanding and even a quantitative understanding of how it works. So I'm just going to show you how we do the natural analogs, how we do the modeling, a little bit about the experiments. This is the phase we are in today, and how we try to make that into a conceptual understanding of what to do. Okay, so if we start with the H2S chemistry of natural geothermal systems, okay, the problem here is the chemistry of sulfur is very complex. So it's found in many oxidation states from the H2S, hydrogen sulfate, all the way to sulfuric acid. So the oxidation state of H2S, sulfur in H2S is -2, and the oxidation of sulfur and sulfuric acid is +6. So we have lots of compounds between. And this is a particular problem because we find all of them in geothermal systems. So how do they play together? How are they somehow related? This is all the basis of the understanding of the chemistry of sulfur in the systems. So you can basically subdivide the sulfur chemistry into 3 parts. It's the speciation, so what are the compounds that we see? What is the chemical forms of sulfur? And how do they react between each other? Then we are interested in the source of sulfur. Is it coming from below? Is it coming with the rainwater and so on? This is maybe a more of a general interest as well. And then the key part here is to understand the reactions between the different sulfur compounds and the rocks. Okay, so that's the general approach here. So you can say behind every single thing here is a specific project. And I can give you an idea of the extent of a project like this. So the sulfur speciation, that was a full PhD project. The source of sulfur, that's another PhD project. And this one here, it's actually 2 PhD projects. There's a tremendous work behind this, even though there's only one diagram at the end. Okay? So just to start with the sulfur speciation, what are the forms in the geothermal waters? So this was the project of the basis for what we did later on. Basically started in the 2006, 7, something like that. And it basically involved trying to analyze all the sulfur compounds within geothermal fluids. So as I said before, they range from H2S, this is what we are interested in here, all the way to sulfuric acid. Some of you know maybe sulfur dioxide, that's what often comes with the volcanic gases and so on, but there are many, many other things here. Thiosulfate, sulfite, polythionides, elemental sulfur, we know that, that's the yellow stuff often associated with geothermal stuff, polysulfides, and then they all react with each other. I'm not going into details how that works, but the important thing here in geothermal fluids in Iceland and actually worldwide, it's the same, we have tried to do the same thing in other locations. We have mostly 3 guys present in geothermal fluids, and they react with each other, H2S, sulfuric acid, and then thiosulfate. And I mentioned here at the start that one of the things that actually people try to do when they're cleaning H2S at the surface, it's actually to convert the hydrogen sulfide to some of these other guys here that are less poisonous and stable. Most commonly, it's either elemental sulfur or all the way to sulfuric acid. The reason for that is that sulfuric acid is something you can sell. Okay, that's the main, it's an economic value. Whereas the rest of them, they have much less of an economic value. So, and so these 3 guys, they are present in the geothermal water, and then in the steam, we have also H2S. So in the water, we have H2S, sulfate, and thiosulfate. So hydrogen sulfide, sulfate, and thiosulfate. And then in the steam, we have hydrogen sulfide or H2S. This is where the smell comes from. So that's how it looks like. I'm sorry, this is just the data points and doesn't maybe tell you a lot, but this is a little bit to somehow help you visualizing this. So this is sulfide. This is the guy that we are interested in. Okay, that's all here as a function of the other one. So this is sulfate. This is sulfate, and thiosulfate. So basically what you can see here is that predominantly you have sulfate, okay? And then you have quite a lot of sulfite, the H2S, okay? So low sulfuric acid, a lot of H2S. Relatively low H2S, you have often a lot of sulfuric acid. So they come together, and this makes sense. You either have an oxidized or reducing environment, okay? But you can see there's not necessarily a logistics in this, at least not easy to see to start with. Okay, so what is the source of sulfur? This is something that is a continuous debate within the world of science. So where does it come from? Does it come from the mantle? Does it come with the rain, from the seawater, and so on? This is not maybe so much related to the sequestration of H2S, but it's of a general interest in terms of the sulfur chemistry of geothermal fluids. So we have spent enormous effort on this, particularly in Krafla and Reykjanes, to try to distinguish where the sulfur is coming from. And basically, we have two sources of these guys based on sulfur isotopes. We either have sulfur coming from the mantle with the magma, so it's a degassing sulfur from the magma. And the H2S in natural geothermal systems seems to be entirely coming from the below, if you want to. And has a very similar values as the mantle. Okay, this is the same with other compounds like CO2 as well. Sulfate, the sulfuric acid in this system, here, the SO4, it's a little bit more complicated. It either comes with as a marine source from the seawater or with the rain, or it is produced upon oxidation of this mantle-derived H2S. Okay? So that's how it looks like. I don't know if it tells you a lot, but here you have the seawater. This is the sulfur 34 in the geothermal fluids at Krafla and Reykjanes. Here is mantle value, that's 0. The H2S actually added together, the vapor phase and the liquid phase becomes almost 0, whereas the SO4 has a range. So midway from the H2S to the seawater here. So that has a double source. Okay, so how does the H2S react with the rock? Basically, to summarize that, I didn't put any pictures of how this looks like. They are just a little bit abstract maybe. But the H2S concentrations in geothermal systems, they are considered to be controlled. The concentrations are considered to be controlled by interaction between these fluids that bring the sulfur from below or the surface with the alteration minerals. And then the H2S concentration may be then affected by boiling and cooling. So basically what you can say that within the system, you can see here is the melt, here is the H2S coming originally up into the geothermal system, and then here the H2S reacts with the surrounding rocks that basically buffer the concentrations of the H2S here. The sulfate is then produced either upon oxidation of this H2S, or it is brought in with the surface water. It's either seawater or rainwater with a sulfur from the sea. Okay, so what is the process of this H2S mineralization? And I'm going to give you a little bit insight into how we do this modeling. Again, it may a little bit be difficult to follow, but I'll try to somehow set it up in such a way that it is easy to see at least the points. So what we are trying to do is we are trying to go back into the system here, look at just a small box of a rock plus this fluid, and simulate how they react in terms of the chemistry to see how the rock is actually eating up the H2S. So you can say that you have water and H2S within a matrix of a rock. So these would be the rock fragments. These would be the pores between the rocks. And then the fluid flows here, around here, reacts with the surface of the rock, dissolving it and forming some secondary minerals. And it's exactly this guy here, the green guy here, which is the secondary mineral, that we want to enhance in terms of the sequestrating or mineralizing the H2S that we inject into the systems. So the overall reaction that we are basically trying to simulate in the computer is dissolving the rock by water and hydrogen sulfide, forming secondary minerals, and then there's always a leftover. We call it solutes or dissolved elements in the fluid. Dissolving this guy here by the water percolating through and forming this guy here, the green one, so to speak. This is straightforward, okay? This is just applying physical chemistry to the whole thing, where you introduce the solubility of the minerals and the rates, how quickly they dissolve or form, okay? So in terms of chemistry, it's not so complicated to do. The problem is more how to choose your system. What is the composition of the rock? What is the composition of the secondary minerals? And then you can apply that to these types of calculation functions. So basically what you can follow any of those one here, okay, as a function of your reaction. So basically I'm showing here this part here. This is what we're interested in. We are interested in injecting the H2S into the surface and changing it into secondary mineral or sulfides. So basically what you have here is how much rock you have dissolved, and this is how much secondary minerals you have formed. So each line here represents the calculated quantity of a given secondary mineral. So this is at low temperatures, okay, and you can see that you get the typical minerals: quartz, epidote, albite, prehnite. You have even some viracite and chlorite and etc. in here. But there is very little at the low H2S. This is low H2S concentrations. So very little sulfides forming. Okay. If we then inject so you can say this is almost like the natural background level. Then we inject the H2S we are interested in. We 50-fold the concentration with injecting the locally, at least at the outflow of the re-injection well. And what you can see here, the same thing again, how much rock is dissolved, and then how many secondary minerals are formed, how much of this has been dissolved, how much of this has been formed. And the one that you have to focus on is the orange line here. Okay, these are your sulfides. So basically what happens is that almost instantaneously the rock starts to dissolve, forming many secondary minerals, including the sulfides, when you inject the H2S into the systems again. And they will continue doing that, until you have reacted quite a lot of rock. You can try, moles is maybe a value that is a little bit difficult for many of you to think of. 1 mole of basalt is approximately 120 grams of basalt. So you have to get to this value here, you have to dissolve 100 or a little bit more than 100 grams of basalt. That's maybe something like this in a liter of water. It's quite a lot, actually. But eventually, if you dissolve almost 500 grams of rock, you have mineralized all the H2S. So you get quite an effective mineralization reaction. The system will eventually eat up your H2S, but you need to react quite a lot of rock to achieve that. We've done lots of this as a function of sulfur concentration, flow rates, temperatures, and so on, and try to optimize what are the best conditions of injection. And this is how the overview of that. This is the suggestion we actually gave, and that triggered the Sulfix project, if you've heard about that. That is being started at Hellisheiði, for example, now. So this would be the line here, the blue and the red line,
these are the natural backgrounds. This is where you want to get. This is your goal. Okay, you want to change your disturbed system back to your natural system. So think about your line here as your background. Okay, it's the same here. Okay, and then you inject two types of waters. This is two scenarios. This is actually taking 10% of all the H2S from the Helliseiði power plant and re-injecting it. This is taking 100% of all the H2S at the Helliseiði power plant and re-injecting it. And then you can think of, you can re-inject it within either outside or on the side of the system at a low temperature in the recharge area, or straight into the system at much higher temperatures here. Okay, so you can think of the two dots here, re-injection at two different temperatures. Okay, so if you inject a lower 10% value here, you will have to react, and this one here is 1 mole. The arrow here and this one here represent 1 mole of reaction. It is how long takes from here to here. Okay, that's the size of the arrow. So basically, if you inject 10%, you will, by dissolving 1 mole, 100 grams of basalt, reach back to the ground zero level, back to the baseline level. That's where you want to get. You have mixing as well if you are outside the system, and it will probably mix. This is the dilution or mixing ratio, and this would probably be the optimal path in terms of that. And back you get to the producing values here. In case of injection, 100% of the things in here is that you will need 1 mole to get down to here, okay, which is not so far if you have some mixing back to the background levels, okay? But if you inject it straight into the system, you're here, and you need a lot of reaction to get back to the ground zero level. So the way of looking at this is that if you inject the system in 10% or relatively low concentration of H2S, it really doesn't matter where you inject it back in. You will eventually, hopefully, or you will eventually, at least theoretically, reach the baseline value. In case you inject much higher concentrations, much more, it is more feasible to do that at the lower temperature within the recharge area, where you have a much more reactions in terms of forming the sulfides, and then you have dilution occurring as well, back to your baseline level, than at the high temperature values. There is the reason for this, why it is more effective at low temperature than high temperature, that's quite complicated. It relates to that there are competitions between different mineral reactions for the same elements. So sulfides, they want to get iron, they need iron, but there are other minerals that also are competing with iron. And the key guy that is competing with sulfides for iron is epidote, and the epidote starts to take over at the higher temperatures compared to the lower temperatures. So that is basically the idea behind here. This, however, here, this diagram here, this is basically an exercise. This is a computational exercise. There's a lot of assumptions behind this, and the results partly depend on what you put in. So in terms of verifying this, before we start actually full-scale injection, we want to scale it up. This is the approach here. So the next approach in this is where we stand today, basically, and I'm going to show you a couple of slides on that, and then I'm over, is that we try to do exactly this thing, try to simulate exactly these pictures, but not within the geothermal system itself, but within a laboratory-type geothermal system. So this is just our geothermal system. This is a reactor, okay? There are many different types of reactors in my lab. This is one type of it. So basically, we are doing the experiments in a reactor like this. This is just, it's about the size of the can here. So you just put the rock in here, put your H2S, the water, close, heat it up, pressurize it, and then you just follow the reactions by opening it and looking at it, taking samples, and etc. So basically, you want your scaled down system to mimic your computational exercises, and then you scale that up to the natural system, so to speak. So this is where we stand now. Okay, it's actually quite promising. We are studying the same reaction as before, the rocks dissolving by water in H2S, forming some secondary minerals. In this case, we can look at the secondary minerals. This is the guy we are trying to produce in terms of mineralization of H2S. This is pyrite. These are other guys. This is chloride and some other clays and epidote and etc. We can also follow this part of the formula here, okay, the dissolved elements. And this is maybe what we are trying to do here. Here you have your H2S concentration in the water, and you want to take that down, okay? And you can see that it's not always as simple as that. Sometimes it goes up and then down. Sometimes it goes immediately down. It depends on exactly what you're doing, and this here is all related to what I was talking about to start with. It's the different compounds of sulfur. It's not only H2S, it's doing lots of other things going back and forth. So basically we want to bring the H2S down back to our baseline level that we define by looking at the natural systems. And then we put it all together, and there is some kind of a suggestion or recommendation of how to basically do this. If it is feasible, if we should abandon this, if it takes too long, if it is something that could work in practice. And then this is simply just scaled up within a test in a geothermal area. And the H2S test is just about, it started this summer, and then they're going again soon, again. Okay, so this is just to wrap it up. So H2S emissions, they are a problem or a growing concern associated with geothermal utilization. There are many possible ways of reducing or dumping this H2S. One of the options that we can try to use, and has never been tried before in geothermal or anywhere as far as I know, is simply to re-inject it back into the system. Okay? This is a low-cost method, but there's a high risk because we have never done this before. So in order to reduce the risk, we have started and are still in the progress of doing an assessment based on the geochemical aspects of this, trying to model, doing experiments and comparing that with what we see in nature to see if this is a feasible thing to do or if this is something that will actually affect our geothermal system in a bad way. So change the composition of the fluid, change the production chemistry of the fluids and so on. So far, the results are promising, but there is still quite a lot of work to be done, particularly on the experimental side and then scaling it up to a large-scale geothermal system. This is something that we are doing in the next 2-3 years. Saying that all, I don't do much of this. I just do the admin work and fill the bills and pay the salaries and so on. So there are lots of people that are involved in this, and this is how projects like this, at least in where I come from the university environment, are run. So I am here doing some of the experiments and isotopes and lots of the modeling sometimes and so on, and then keeping up the spirit. Soo Hye, he is a professor at MIT. He is the other side of this, looking a lot of the natural systems and so on. But basically, the driving force of this, they are students and postdocs. So Hanna, she is from Finland. She is a postdoc here with us today. And this is not Hanna, this is Nick. At least the picture is of Nick. So Nick Keller. She is Swiss, she's a postdoc as well. And then Njói, he is a student with us. And then Snorri, he graduated just last week. He finished his PhD last week and is now a postdoc with us doing, and he is the guy behind the experiments. So thank you very much. And I want to thank the sponsors here. It's University of Iceland, Landsvirkjun, Georg, Reykjavík Energy, and Ranís. These all sponsored this project. Thank you very much.